Welcome to another video from KOJRO, and this time it's time for the episode 9 in the Resurrection series. And this time we are going to talk about the C64 power supply, and this is an example of the earlier ones that was with the bread bins. And I'm going to talk about this from an European and strictly speaking Norwegian perspective, because all the power supply I have is either sold as new in Germany or in Norway. And I know that some of the power bricks that was sold elsewhere, and I've seen YouTubers present American power supplies, and they are slightly different. Every region has their own rules and regulations for power supply, so of course that's going to differ. But the most noticeable difference is the countries that use the 110 to 120 volt system, as we in Europe use a 220 to 240 volt system, so that's the main difference. This is the power supply that I grew up with. Some earlier C64s had another power supply. That was a small black box. I do think that this was only valid for about a year or so, or maybe not a whole year into the C64's early days in Norway. And then when the C64 of the newer ages come, it was this one that took over. And I'm going to go in depth both on this power supply and on this power supply. And on this power supply there is a lot of different versions. They all look about the same, but they are slightly different. And also the power supply for the Commodore Plus/4 computers used power supply that's totally similar to this, only it's black. I do have one of those also, but I'm not going to break that apart. And this power supply is slightly bigger. It delivers more 5 volt than this one, and that is because the newer C64s does not rely on the 9 volt AC to supply the SID chip and other chips in the metal can inside, so they need more 5 volt draw. And also some of the cartridges that was coming for the C64 required more power. And that is also why when the memory expansion units for the C64 was launched, they had their own power supply that came with them. And I'm going to go in depth in these power supplies. I'm going to take them apart. I'm going to analyze the circuit. I'm going to try to simulate or see what happens when different things break in these power supplies. And this time I'm going to start with this kind of power supply. And this kind of power supply, as I said, I grew up with them. And you can see the wedge shape on these. I grew up in the north of Norway in a rather cold house, so I always wished that the Commodore 64 was supplied with 2 of these, so that I could warm both feet beneath my desk. But this we are also going to go in depth on, and we are going to do some slight modifications on the power supply tester as we go along. But we won't be getting into this kind of power supply in the first part, and I'm going to break this up in several parts to make the videos a bit shorter, and also to be able to focus on 1 or 2 elements in each video. So that's the plan for today's topic, and I'm also going to look into some of the possible faults that can happen with this power supply, and if they are dangerous to your C64 or not. And as you can see in the main video screen here, I'm taking this power supply and making it into small pieces. I'm going to make every part of this accessible so that we can measure them and take and make an exact schematic of how this is coupled. And we will also do the same with these ones in a later episode. As you can see, I am trying to break away all the epoxy that's covering the circuit board, so I will be able to desolder the components and take out the printed circuit boards to inspect what's beneath it. And here I can already see one fault with this power supply. And this is the power supply I got from Tommy at Arctic Retro. One of the legs on the capacitor, the big filtering capacitor, is almost etched away. So this capacitor has certainly been leaking. And this epoxy has certainly not been weakened by the passage of time, because this is rock solid and it's kind of difficult to ship this out, and I'm really worried about destroying what's beneath the circuit board and also cutting some of the wires and stuff that goes into the board. I'm getting close, but there are still some epoxy that's covering the edges of the board and also the board itself in some places. And this epoxy dust really has some sharp edges, so it's important to clean the desk and get rid of this as I go along. And now it's time to connect this up to my power supply tester and both test the power supply tester and the power supply itself to see if we have more faults to iron out on the power supply tester design, and that we probably have. Yeah, and I used my trusty old Metex to measure up this, and sorry about the picture quality here. I am holding both my hands and the measurement leads on top of the display on the multimeter, and that's of course not good. But now I measure about 8.6 volts out of the rectifier, and I measure the same as input to the voltage regulator. And also about the same when I measure on the capacitor contacts for the blown capacitor. And this extreme secretive measurement is made on the output and on the leads outside the creds, and it shows 7.01 volt, the same as we had when we measured on the plug earlier. But on our board we measure 0 volt. That can't be right. So that means that there are either a break in the cable or our circuit is handling the 5 volt rail wrong in some way. And I find that very strange. But I turn the board around and I measure the same on the pins that come straight from the connector for the power supply. And that means that it has to be the cable or something else that I haven't thought of. And I do know that this plug is working because I got voltage on the other power supply. And with plug I of course mean the socket. And I'm nothing but consistent. I always manage to hold my hand over the display when I measure this, but this is 7 point something volt when I measure on the power supply. So I started to investigate the different cables on the PSU that I have laying around, and I took a picture of 3 of them as a comparison here. And this is from a white power brick from 1989, and this is the newest one I have laying around. And here you can see that all the pins are present on the plug, and this is the only C64 original power supply that I have that have all the pins present in the plug. And this is from the white power brick that I got from Tommy on Arctic Retro, and the one that I pulled apart first. And this power supply is made sometimes in 1987, if I remember correctly from the date stamp on the back. This is from my old wedge power brick from about 1984, I think this one is. And this is what I call the foot warmer. And as you can see here, they've changed the pins around. So on the white power bricks, they use the pins 3 and 4 for power supply. But on the older ones, they use pins 3 and 5. This is from the original C64 schematics, and here you can clearly see that pin 4 is stated as not connected, even though on some of the newer manuals for the C64, it's stated that pin 4 is 5 volt DC or not connected. And this is from a slightly newer C64 schematics, and here you can see they have changed the pinout somewhat. They say that both pin 4 and 5 are 5 volt. I have not checked this on the PCB on and really old C64, but it's clear to me that if this schematic is correct, the white power bricks, they won't work on the oldest C64 because they are not able to supply the 5 volt on the pin 5. So this came as a slight surprise to me. I didn't think of this at all. I have never noticed, I've never seen anyone actually mention this before, so this was a complete surprise for me. And so to my initial diagnosis of this circuit, as I've told you and as we saw in the pre-processor to this episode, the output that we measure from this power supply is about 7 volt, but when we plug this to our tester, it only shows at 0 volt and the voltmeter. And I thought that this was because this regulator was acting as a non-linear resistor that increased the resistance with the load. So that could explain the 0 volt on the tester, but this was clearly a case of Occam's razor, where the solution was that I have only connected pin 5 and not pin 4 on the PSU tester, so the power supply was not supplying the circuit with power at all. So that was the first fix of the day. I soldered this wire from pin 5 to 4 to have both possibilities covered and each scenario. So I have to add that I did not discover this fault with the cable and the different plug layouts, until after I had desoldered and broken the PCB on the faulty PSU. So what I'm first going to do now, I'm going to solder the PSU back together to have the original fault situation again. But before I start any soldering, any repair work or any more fault finding work, I will draw up the schematic for this power brick, as this power brick is slightly different from the normal foot warmer bricks that I'm used to. Yes, I'm back in the shed and I'm again going to look into these power supplies. And the first thing I'm going to do is, this mess has to be cleaned up, and then I'm going to draw a quick schematic of how this power supply actually looks from an electric point of view. This epoxy really has some sharp edges to it, so I'm a bit careful with this cleaning. What we see here in this power supply is this output here from the transformer. And this is not the same transformer that is in the foot warmer kind of bricks, the original beige power supply, because this has 3 windings on the secondary side. There is one winding here that goes straight to the 9 volt into the C64, and then you have 2 windings here that supplies the 5 volt. And this does not use a full bridge rectifier. It actually uses a trick that these windings come out in opposite waves. So this schematics for this, I have not gone into any detail with this, but you have the primary side of the transformer here, like so. And you of course have a fuse here before you connect this to the mains. And then you have the transformer here with 2 windings, and they are coupled like this, and you have one rectifier diode that's connected to each of these planes like so, and you just have the commons on this middle wire, and you have the other 2 windings coupled like this, and these are actually shorted together on this side like so, and there are no components connected to these 3 places here on the PCB, but over here you have a small capacitor, and you have the large capacitor over here, and you have one resistor over here, one resistor over here, and you have a small capacitor over here. So if I draw this, it will be something along the lines of this, probably along the lines of 2000 microfarads or something. I we'll try to measure this one that's in the power supply that's working properly. And this then gets fed into a power regulator or voltage regulator. That probably is something aligned the 7805 or something. It's probably not a 7805 chip, it's some variant of this. And this pin is normally grounded on these power supplies to give out 5 volt. But here you actually have the resistor network here to provide a slightly higher bias voltage. And that is why these power supplies gives out about 5.2 volt. And I have measured these resistors that's down here in the epoxy, and this one 3.3 ohms approximately, and the other measured 100 ohms, but I will check this on the other power supply. Yeah, this is about 100 ohms and this is about 3.3 ohms. So that means that the resistor that goes from the middle pin here, like so, the middle pin here, and down to the output, it goes like so, just stands in between these two windings here, one resistor, like so. This is the 100 ohm resistor, and this one goes from the middle pin and down to ground, and that is 3.3 ohm. So that means that the ground plane here is connected through this 3.3 ohm, and that we also have a small capacitor here before we feed this to the output. So how does this work then? Why are we having these resistors in the circuit? And I can give a quick explanation on this. This power supply is meant to give out a voltage that's slightly higher than 5 volt, and that is to compensate for the loss in the cable. And we have the unregulated 8.6 volts, or from 8.4 or 8.6 into the voltage regulator. And this is an ordinary kind of TO220 regulator, something along the line of a 7805. And this circuit is meant to have the middle pin grounded, and that is because this has an internal voltage reference, and this voltage reference is referencing the voltage to 0. So what we are doing here is that we raise the voltage to the ground pin, and the ground pin is, as we said, the reference. And we have a voltage divider here, which we can use to calculate how much the output voltage is actually affected by this. And a simple calculation, and this is not totally correct because we have some power going into this, or some milliamps or microamps or whatever going into this pin, so the current through this resistor and this resistor is not the same. But this is approaching 0, so we can about neglect that. And what we then have is we have the 5 volt, and we have the additional voltage that we have raised this pin. It's 5 times 100 over 3.3. So with this resistor network times the voltage, and you add the voltage, and you came to 5.17 volts out of this, and that is about right. You can get between 5.16 to 5.2 volts out of this. And of course this resistor is not the highest quality, and they might increase their size by age. This is quite a common way to do this, but most of the regulators in the 78 series actually has an application note that says that this is not how you should do this. You should choose a regulator that gives you the voltage you need. But this is quite okay. I've seen a lot of circuits doing this, and it actually works. But you do get some power loss in this. It's not a huge power loss, because you have this through 103 ohms, but it's 5 volts. The current is the voltage divided by the resistance. And if you do like this, you see that it's 48 milliamps that's drained to this. So you lose 48 milliamps, and you're losing about a quarter of a watt in these resistors. So of course that's also power draw that you draw through the regulator, and you also drew it through the transformer. So this increases the heat in the circuit. But all in all, my biggest concern is that this regulators in the 220 cans has 1.5 amps as the maximum current. That's something you're only meant to draw if you have about an infinite size of the heatsink on this one. And we also have a small capacitor here on the input, like so. And these are probably just 0.1 micros or 100 nanofarads or something. They are just there to make that the circuit does not oscillate. So I think this will look something like this on the schematic. And then you of course have here a separate winding that goes like this to the output and is 9 volt AC, and this is 5 volt DC, or 5.2 volt. So this is the circuit that was here, and the fault in this power supply was that this capacitor was removed. And because I've desoldered all of this, it's difficult to reshape that fault condition to make a good and viable test on this power supply, to test how this actually was without this capacitor. My initial thought on this was to reuse this PCB and mount it back in, but I soon gave up on that, and I'm just going to solder the leads back together as a harness. Yeah, what I'm going to do here is that I'm going to use some copper wire and just bend it so that it fits together in approximately the same way as the circuit traces on the PCB did. So I just take this copper wire and bend it and try to solder it to the legs as best as I can. Yeah, and I know this copper wire is kind of thick, but it's the only uninsulated wire that I had in pure copper, so I'm going to use this. And this is the power in circuit that I'm doing, the unregulated side from the rectifier and out. And when I'm about to solder this, I actually discover something quite important. This epoxy that is contained within this power supply do actually have quite a good thermal efficiency, as it cools down the metal that is in touch with it quite effective, and that's showing on the soldering. I has to use a lot of heat to solder everything that is in contact with this epoxy. But that was the power input. Now I'm taking the ground wire, and the ground wire goes from the common on the transformer and to the capacitors and to the grounding point for the resistor on the middle pin. We also solder back in place the blue wire, and the blue wire is the ground connection, so that we can use the power output on the plug. And then it's time for the middle pin on the regulator, and here you have the resistor network and one capacitor that is connected to this. But this we use just a thin wire for. Actually is the leg from an old big 4 watt resistor. For the output pin, I use a bit of isolated wire because this needs to be pretty close to the aluminium heatsink that's inside here. So instead of using heat shrink to isolate it, I use this wire. And this is only 3 connections in addition to the lead from the power plug. As you can see, it ain't pretty, but I do think it will work. So we have to now take some measurement to see how this actually works out. Have we recreated the old fault with about 7 volt output? I am always skeptical with plugging in something like this into the mains, but this is protected by a fuse, so I don't think we will do any harm even if we have done something wrong. And this is not right. It should be more than about 3 volt here. This should be the 7 volt that we had initially, but I do have a suspicion here. I do think there is something wrong with the soldering, so that we only get half of the sine waves that we should into the rectifier. Yeah, we all saw that, didn't we? We only had 3.5 volt on the multimeter, and what we have when we have a transformer that transforms the 50 Hz sine wave from the mains into a secondary winding, we have something that approximately sinus, and we do have some distortion in it, of course, because it passes through a drossel and also some capacitance inside the windings. With a full bridge rectifier, we will expect to have the sine wave to be only breaking up in the positive halves here, and the negative halves will be turned into positive ones here. So we only get curves on the positive side of the amplitude. But with just one diode and one winding, we only get simple rectifying, and that will be represented with the curve down here, where you see that every other curve on the sine wave, when the negative curve of the sine wave will just be cut away. And of course this is not totally true, because you will have some overswing and underswing in the zero passing here. You also have some other artifacts that can happen when you rectify something, but it will not be like this. And this is why we only measure half of the voltage that we expect. It's because we only have half of the curve with us. And what the fault actually is, you can see down here in this red ring. I connected these pieces together, but this joint was so bad that when it came under tension, it actually broke, so that the diode did not have contact with the copper wire here, and that means we only get one of the windings to supply the circuit with power. But with that remedied, we could continue to measure. So after fixing this and soldering that joint there, I'm going to take a new measurement, and I've connected this and it's all over the place. But if I measure now from the ground lead to the positive, yeah, I have the 7.1 volt, so now we have recreated the fault from before. Yeah, but let's take a quick peek of this on the oscilloscope, and we connect this to the output, and the yellow wire is the ground wire. And sorry for the flickering here, but it's only 50 Hz, so this is an analog scope. And it's 2 volt each divider, so this is about what we expected. And here we measure the input, and the input is slightly higher than the output, but it's very clear to us that the regulator does not work. It's also quite clear that we have little or no use of the small capacitor that is left here on the input side of the regulator. So we clearly have to do something about this, and the first thing I'm going to test is to add a capacitor. But now this video has gotten way longer than I thought it should, so I will stop this here and we will start a new video by doing some experiments and introducing some fault and some fixes of this power supply. Yeah, so that's it for a video that got far longer than I really thought it should. So thanks for watching. Please hit like and subscribe if you are somewhat interested in what we have to say on this channel and want to be notified when we post new videos. So, thanks for watching. Hope to see you in my next installment in this series that will be within a week or so. See you then.